We'll crop it when
Yeah,
we
yeah, yeah.
do the thing. We can also start like on your timer as well. Do you want to start your stopwatch? If you have battery,
Yeah, yeah.
it's okay if you can't.
We need this, I think.
Probably,
It's
yeah.
easier.
Okay. All right. Three. That one. Okay, 3, 2, 1. Go. Hello. We are. Okay. Fine. This is. Okay. We'll start with our names. Names is good.
Yeah.
Okay. Hello. I'm Sharwin.
And I'm Saitini.
And our project is robot racing using visual inertial odometry. So the goal behind this project was to build a sort of racing simulator slash game to allow the user to generate their own trajectory and then race against it afterwards. The trajectory was mapped with visual odometry using a camera, and this kind of emulates existing scenarios where you have a race car driving against itself or another driver in a ghost scenario. So here we can see Lando Norris's orange car is in Ghost, and the Charles Leclerc's red car is a real driver, and the telemetry data for Lando Norris's car was taken and evaluated and synced with Charles Leclerc's car for the same track, and is overlaid, and that footage is overlaid with the real driving footage here, so viewers can enjoy seeing a driver race against another driver in real time at the same exact location, without the two drivers obviously being there. And so, just to talk about our previous approach to this problem, previously we attempted to implement the whole pose graph optimization pipeline using an Intel RealSense camera, which is an RGBD camera, as well as using OpenCV libraries to perform the feature extraction, odometry estimation, loop closure detection, and the pose graph optimization itself. And the visual odometry struggled without sensor fusion with the inertial measurements from the IMU. The IMU provides more robust and accurate pose estimation, but also suffers drift over time. Visual odometry suffers from feature management, and the lack of features disappearing or popping up can dramatically affect the pose estimation, but is robust to long-term scenarios and is good with the feature-rich environments. So fusing the two, we can get the best of both worlds, and we were lacking that in our implementation. Another thing that we were lacking was confidence metrics, and this is basically once we actually evaluate the pose from the feature matching, how confident is the algorithm that the estimated pose is correct. With this confidence, we can essentially choose how much we trust the resultant pose that we get, and then we can perform our update according to that probability. Without that probability, our pose will always update regardless of how absurd the pose estimation it received. And so here in our previous implementation, you can see the RealSense camera being moved, as well as all of the nodes in the graph being published. And if you look at the feature, tree, you can see a lot of features disappearing and coming in, and this kind of disappearing features is what creates this dramatic shift in the pose estimation.
So what we are implementing now is using the Z camera. The Z is a much powerful and a very high compute camera, and it has its own visual inertial odometry implementation and a wrapper for ROS2, which we are currently using in C++. So what you could see in this image is from the official documentation of Z, where the Z camera is moving in real world and how the movement is being captured using the RVS platform. Z also has a property of using Kalman filters and confidence matrix, as Sharvin mentioned. So it's much more realistic, and the physical world and the physical the inefficiencies are being modeled. That's why it's much more accurate, and the IMU data is also being fused. So this is our current robot setup. This is the turtle bot, the same bot that we used before. And this is how we are publishing it to the Arvis. Arvis is like a visualization system for us, which helps us to see where all the transforms are and where the relative positions of each of the elements of the robot or the camera and what the camera can visualize. We'll show you the snippets of Arvis in the later presentation slides as well. And yeah, so why we chose the turtlebot, because it's a differential drive robot and it doesn't move sideways. So the only way it can drift from the current frame is when it slips, which is not a very common occurrence. Therefore, the IMU data could be much more reliable than if we use some other, like a legged system or any other system that has like a omnidirectional movement or a steering wheel movement. So I'll show you the setup as well. Yeah. This is the turtle bot, and here we have mounted using a 3D printed mount, which holds the Z camera, and it also has a lidar. It all has a IMU and some motor controllers. We are not using the lidar currently, but in future, if we want to improve our previous approach, we can consider fusing the IMU sensor data and the lidar data to give us a more accurate odometry value. We could also use the encoders from the motor to get a more realistic physical emulation of our system. But Z on its own independently is good enough for us to not need to fuse any other raw sensor data as well. So this is the complete system design which we are doing currently in the present system. The turtlebot that we just showed you with the Z2i, we extract the camera pose. So for this extraction, what we use is that ROS, if we run a software development kit inside the turtlebot, it publishes the raw data, and we are able to subscribe to that data using C++ ROS wrapper that we mentioned, and that's how we get the frames of each timestamp. Then that the frames.
Oh, sorry.
So when we get the camera pose, we also get the transforms of each frame. So the feature extraction, everything is abstracted, and Z directly gives us the transforms of each frame, and we combine those transforms into a path, and this is the odometry path. So everywhere we move the turtlebot, we have a whole complete path, and then we extract parts of that path depending upon what we need. So the extraction now works using service calls. Service calls is a feature in ROS which is basically like a API call in other cases, where if we place the trigger of starting or stopping the recording or starting and stopping the racing. So these are the 4 services, and we also have a service for resetting the path. So I'll first explain the start and stop recording. So this is where the service of start and stop happens, and whenever we call the service, we actually save the current timestamp of the system, like of the system log, and then we use that timestamp to index over the odometry path. So that's how so this would be the extracted path from the odometry path using the timestamp, which are the 3 points, and that would become our recorded racetrack. And similarly, you can go to the next. Similarly, we'll do for the racing path as well. So every time we have like a start or a stop, we'll record that time. So now what happens is that because it's a very flexible system, we could record, re-record, play the same game multiple times. We could save the initial path multiple times, so it gives us a lot of flexibility. Like, for example, if we have the service call after this, we could save the recorded part after this as well. So
Yeah,
then
and so like Anthony mentioned, we have both of our paths, which are extracted with our timestamps, so we can do them reliably and also repeat them later on in the life cycle. We don't necessarily need to restart the whole system to extract a new path. And so now this leads us to our the next part, which is really critical to the game and also to evaluating both of these paths. So when talking about evaluation of a pose trajectory or a path, there's two main methods. There's absolute trajectory evaluation and also relative trajectory evaluation. The metrics here on screen are all absolute trajectory evaluators, meaning that they evaluate every pose in the global sense, in the global frame, and evaluate the entirety of the path to each other. And so there's three up here: root mean squared error, mean displacement, and final displacement error. We found that root mean squared error performed the best and provided accurate results that also seemed realistic and also intuitive to what the user would expect when racing against another path. To quickly cover over these three different metrics, root mean squared error basically provides a normalized average of the translational distance between every pose in both paths. This provides a strong correlation between the matching of a reference trajectory to the actual trajectory. However, it will heavily penalize large deviations. And so moving far away from the path at one point, then still coming back, will penalize the path a lot. And so a lot of the paths that we have are actually penalized a lot, even though they match somewhat closely. Next, we have mean displacement error, which is similar to root mean squared, except we're simply taking just the average displacement over the whole path. This weights every pose independently or equally, and this can be more robust to outliers. However, it will also, again, create this kind of problem where small outliers will create a diminished reward. And so if you deviate from the path a lot, you're still going to see that same accuracy fall. The last metric is final displacement error, which is very simple but also not very conducive for mobile robots because they travel through the world. And final displacement error simply compares the final location, and so the rest of the path does not matter, but just the final position of the robot and the robot's trajectory and the reference trajectory. The second method of comparing these metrics is with relative trajectory evaluation. And so what that would mean is basically comparing the individual transforms between every pose in both trajectories. And so you have corresponding transforms in both trajectories, and depending on how much those transforms differ from each other, we can build a relationship of how closely one path matches the other. And that independent and that local transformation difference or evaluation can be done with one of these absolute metrics like root mean squared error. And so now we'll move on to our demo, which we can talk about while it goes on. So the first phase is the race trajectory generation, where you can see the user is teleoperating the robot and not looking at the robot and just creating this race trajectory after calling the service call to start recording.
Also, this is the arbitration concept. So this is the iris visualization that we were talking about, and this is the feature extraction that the Z can visualize and extract from. And the pink part is the racetrack, and the transforms that you visualize are the odometry, and this is the current pose of the robot.
And the next, while this plays again, we'll just talk about the next section. The next section is once the recording is done, the race actually begins. And so the user can either drive back to the beginning, or we can manually move the robot to the beginning of the odom frame or the starting position, or move it to any other position and basically start the race, which we'll see here. And we'll see the pink path come up again, and now with the score, with the red path showcasing the actual trajectory.
And how the paths align, how much the alignment would determine how much score we get.
And because the path score is normalized with root mean squared error, we can actually display it as a percentage error.
So future work that we plan to do, there are a lot that we could improve on. So the controls could be using a joystick, which would make it more intuitive. And we could also have a VR or a AR headset, which could control the movement of the robot, which would make it more interesting to play. We could also work on improving the previous visual odometry that we implemented to get an accuracy which is similar to what Z already has. So for that, we need to fuse like the Kalman filter confidence matrix with the sensor raw data, which is either the wheel encoders or the IMU or maybe the LiDAR. But again, we are not very sure how much LiDAR might help. But again, it can extract features, so maybe it could help. But yeah, we need to test it out and see if it does. We can also work, yeah. So the next thing we would like to do for the gaming interface is we would like to have in dynamic environments. Like for example, if we have the path in the table that you saw and then go to a playground and have the same path being followed. So for that, we just need to have the relative poses stored in a way that the world frame can be dynamic, and that would not be a very difficult task to do per se, but that would enhance the gaming experience. Then we could also support storing each of the racetracks, so we could have like a better scoring mechanism that for individual racetracks what's the score of each person, so that would give us more metrics to check over. And yeah, we would talk about
Yeah, yeah, those are some good improvements, and then some other ones that we also thought of was to implement multi-robot racing and support several turtlebots incorporating the same system to all have access to a global race trajectory, or sorry, recorded trajectory that they can all race against. Similar to how the F1 has the ghost car. And that kind of experience would make a really good gaming experience where everyone can control their own robots and get like a score and also get placements. Another way that we want to improve the system is by, like Anthony mentioned, by integrating the visual odometry with other sensors. But another way that we can improve it is by making it verified and coupled with the system dynamics. And so with the differential drive, there's very simple system dynamics. The second order dynamics are very easy to get from just the wheel velocities. And because the inherent nature of the robot, it can't slide side to side. Any side to side movement observed in the odometry estimation can either be discarded or attributed a very low confidence because slipping is very unlikely. And it can also be very easily corroborated with the IMU or the LiDAR or the encoders themselves. And that would dramatically improve the robustness of the system to small deviations, or even when there's dynamic obstacles moving in front of the camera, like people or other robots. And then another thing with the dynamic obstacles is that we could perform even more optimization to basically segment out dynamic obstacles once we identify them as dynamic. So for example, if we have people or other robots, we can perform semantic segmentation to identify the objects using any sort of classical deep learning model to identify it, mask it away, then discard those features when using the features for odometry estimation. And that would also provide robustness to people walking through it and it still being able to track its position. Another point of improvement could be autonomous control and autonomous navigation. Currently, we have implemented teleoperation, and like Anthony mentioned, we want to expand to different forms of teleoperation with the joystick or VR. But we could also implement autonomous control, where once the race trajectory is obtained, then we can have the robot follow it with an autonomous trajectory generator using a curve generator, or users can basically select waypoints to have it follow the trajectory. There's a very high ceiling for the different types of control, but implementing autonomous control could improve the engagement and make it more exciting as a game for users. Thank you. Okay, nice. I think this ended up stopping, but
Oh, 18.
it's like good enough.
Yeah.
Okay. I think it's okay. He said 15
19
to
but
20
4
minutes.
to bro. It's